What's up, mathematicians? Justin here, and welcome back to our course on space, aka geometry. Now, we're currently in Unit 1, which is all about measurement. Our last lesson was an introduction to measurement, and this is lesson 2, which will be proportionality and similar triangles. Okay, we're going to look at the concepts of proportionality, similar triangles, see how they're connected, see how we can use that connection to solve some problems. In this particular video, I'm going to show you what proportionality is, give you a quick example of it, and then we'll use proportionality to measure the height of a tree. I'll show you how you could do that. Now, if you recall, in the last video, I presented some measurement challenges to you in the last lesson. And one of those is to find the height of a tree without directly measuring it. If you haven't done that one, I encourage you to try to do that one before watching this video. Give yourself the satisfaction of solving it on your own. One other note about those measurement challenges that I didn't mention in the last video, but I wanted to bring up now, is I kind of pulled a fast one on you. One of those measurement challenges does not actually involve measurement. Can you figure out which one it is? If so, you can, leave your idea in the comments, or, try to impress your teacher, whatever works for you. Anyway, let's dive into this lesson. So proportionality is a very powerful and important tool for measurement. And since this unit is about measurement, I thought it would be really important to talk about proportionality. Now, there are many examples of situations, many contexts in which proportionality shows up in the context of measurement. I'm just going to look at one. Now, a little bit about me. I love maps and I love hiking, so I thought I'd combine the two and look at a hiking map. So let's pull this up here. This is a map of trails in the San Gabriel Mountains in Southern California, where I live. And I would like to look, let's see, where is it? Here we go. We're going to look at this particular area, which is the area around Mount Baldy, a popular hike. But before we actually do any measuring, because I could measure this map directly, but measuring this map directly won't actually tell me, how far, for example, this, like what is the distance between this point and this point on a trail, because obviously it's only a few centimeters here. So in order to actually measure that distance using this map, I need to know the scale of the map, the proportionality scale. So typically you'll find that, somewhere on a map in a corner or something, and I see it right here. Now, let's see, I gotta grab a ruler here. So I prefer generally to use metric whenever possible. And so let's go with a metric scale. You can see here it goes from 0 to 4 kilometers, and I'll measure how large the spaces are with my ruler. And I can see that one kilometer on this map is 2 centimeters or 20 millimeters. 4 kilometers is 8 centimeters or 80 millimeters. So that's my scale. That is the proportionality of this map. So let's actually write that down before we take our measurement. So let's see. This map has a proportionality scale. Let me bring this down here. So we're talking about proportionality of 1 kilometer for every 20 millimeters. In other words, 20 millimeters on this map is equal to 1 kilometer in the real world. Okay, so now let's look at a portion of a trail that I might want to know the length of. So I'm going to go over here to this Devil's Backbone section of the Mount Baldy hike, and let's measure basically from the summit. So when I hike this trail, I start from here, go up past the ski hut, and then up here to the summit. And then on the way down, I like to take this backbone part, make it a loop, and it's nice and scenic. So let's measure how long it is, and I'm going to go from here to like about here, the straight section. Once you get to here, you're going down some switchbacks, and actually you hit like a fire road too. I don't remember exactly where, but let's measure this section. I'm going to line up my ruler, and it looks to me like this comes out to about 58 millimeters. So on the map, this section is 58 millimeters. Now, of course, it's a little bit of a curve, so it's not perfect, and this is just an estimate. So let's bring this back out. Now, in order to do algebra using this proportionality, I actually want to write it as a fraction. So I'm going to write it as 1 kilometer over 20 millimeters. And now I will write an equivalent fraction using the proportionality of this map. Okay, so I said that the section on the map was 58 millimeters. I want to know the number of kilometers that that section is in the physical world. So I'll go, since I don't know what it is, I'll write in an x. X kilometers. Okay, so once you set this up as a fraction, it makes it much easier to do algebra and solve for your unknown value. When you have equivalent fractions, you can cross multiply them. There are other techniques as well, but that's sort of the quickest one that many students are familiar with, having, once you've made it through a typical middle school math program. So 1 times 58, well, that's just going to be 58, right? So 1 times 58 equals 58. And then I'll cross multiply this way. 20 times x is going to be 20x. Okay, now in order to find the value of x, I need to get it by itself. So let's divide both sides by 20. And these cancel out. So I'm going to get x equals 58 divided by 20. Well, I know that 58 divided by 2, well, actually, we think about it this way. 60 divided by 2 would be 30. So 58 divided by 2 would be 29. But since it's 58 divided by 20, we can move the decimal over one place, and we see that x equals 2.9. So the distance between these 2 points on the map, the distance of that part of the trail, is approximately 2.9 kilometers. Okay, so I promised to show you how we can use this technique, this method of proportionality, to find the height of a tree. So let's set that up and talk through what that looks like. So first I'm going to draw a diagram, and let's see. So we're going to need to have the ground. Put that over here. Okay, and then our tree is going to be, growing up from the ground. So here we go. This is my tree. Very artistic, I know. And in order to measure using this technique, you have to do it on a sunny day. We're going to use shadows as a way to find certain lengths to create proportions to find the height of this tree. Okay, so let's draw in the sun. I'm going to do the sun in orange because, it's a nice sunny color. And so let's draw a ray of light coming from the sun. All right, and then, we've got the sun out. Obviously, the sun is very, very far away. We know that. But you get the idea. The sun is shining, and a ray of light from the sun that just barely clears the top of the tree is at the very end of the shadow of the tree on the ground. So that by itself is not enough to really give us any information to build a situation where we could use this technique, this method of proportionality. But if you have an object or a person casting a shadow at the same time, then you can set up a proportionality. So let's imagine you or a friend is also standing in a position, maybe even positioned in such a way that their shadow, the top of their head, falls at exactly the same place as the end of the tree shadow falls. So this ray of light from the sun just barely clears the top of the tree, barely clears the top of the head of the person, and lands on the ground right there at the end of the shadows. Okay, so now if you know the height of the person and you measure the length of the person's shadow, and then you also measure the length of the tree's shadow, you will actually have enough information to estimate, to measure the height of the tree pretty accurately. So let's go ahead. I'm not actually going to go out and do that right now, but I'm just going to go ahead and use some made up numbers to indicate how this would be done. Let's say that the height of the person is 1.6 meters, which is a reasonable height for a person. And then let's say that the length of the person's shadow is 2.4 meters. Now let's draw in an indication of the length of the tree's shadow. So we'll say that the length of the tree's shadow is 25 meters. Now the only thing that we don't know here is the height of the tree. And this is, of course, the thing that we want to find out. Let's draw this in, and we'll call it x, because it's the thing that we don't know. We'll put that variable in there. Okay, so we look at this situation and we say, well, you know, it does seem reasonable that if this ray of light from the sun is falling, in such a way that these two shadows match up, that the proportionality, the ratio of the person's height to the person's shadow, should be the same as the ratio of the tree's height to the tree's shadow. Now, we haven't proven that, but it certainly seems reasonable. So let's go ahead and use that, I guess, assumption at this point to estimate the height of the tree. So here we're going to set up our equation, our fractions. So the person ratio is 1.6 over 2.4, the height of the person and the length of the person's shadow. And now the tree, well, the height of the tree is unknown, so we put in x, and the length of the tree's shadow, 25. Okay, so we'll go ahead and do our algebra. We cross multiply this, and that gives us, let's see, 2.4x is equal to 16 times 25. 16 times 25 is 40, I believe. And now we're going to divide both sides by 2.4. Divide by 2.4, divide by 2.4. These cancel out. And it turns out that once we take 40, divide by 2.4, you can plug that in a calculator. You're welcome to do that. Or you can do it the long way or do it in your head if you're able to. But you're going to end up with 16 2/3, which is 16.6 repeating. I'm going to round it off to 16.7, the nearest tenth of a meter. So what that means is the height of this tree, our estimate for the height of this tree is 16.7 meters. Okay, so that seems simple enough. However, before we wrap up this particular video, I want to talk a little bit about the assumptions that we are making in doing the calculations in this way. The first one I already mentioned. We are assuming that the ratio of the person's height to the person's shadow is the same as the ratio of the tree's height to the tree's shadow. Well, that's a big one, seems reasonable, but at this point it is an assumption, we haven't proven it. Other things we're assuming that you might not have realized, in fact, you might even try pausing the video and thinking about writing down what assumptions are, but one other one is we are assuming that the tree is perpendicular to the ground at a right angle. We're also assuming that the person is perpendicular to the ground. Furthermore, we are assuming that the ground is flat. If the ground is not flat, these calculations will be off. Now, of course, we know the ground is actually not perfectly flat because, if we're outside, it's never the case that the ground is perfectly flat. But if it's quite close to flat, then the calculations will be, quite close. So, that's probably a reasonable assumption, although if you are on some sort of hill or slope, your calculations would be off significantly if you're using this method. And so let's see, what other assumptions are we making? Yeah, the other assumption that we are sort of implicitly making has to do with the angles of these triangles, okay? So when we see that the ray of the sun comes in, we are sort of implicitly assuming that this angle is equal to this angle. And I'll explain why later, in a minute, and also in the next video. But in order to use this rule of proportions, these two triangles have to be similar. What two triangles, you may ask? Well, you see we have a smaller triangle, and maybe I'll put these in a couple different colors to make it even more clear. Let's start with a smaller triangle. So you see we have this smaller triangle here, okay, made by the person. And then you see we have the larger triangle. I'll try to put this sort of inside, I guess. I'll outline this one in red. We've got the larger triangle, okay? And in order for this rule of proportionality to hold, all the angles in the smaller triangle have to be equal to all the angles in the larger triangle. Well, we know that these two, we've already assumed that those two are right angles. So we can say they're equal. This angle right here is part of both triangles, so it makes sense that it would equal itself. But we are implicitly assuming, maybe without realizing it, that as the ray of the sun comes through here, that it makes the angle it makes with the tree is the same as the angle it makes with the person. Now, when two triangles have all angles equal, as this smaller triangle and this larger triangle do, according to what we've assumed, those are considered similar triangles. Now, in the next video, I will define similar triangles for you and work through a few examples of solving problems with similar triangles. So thank you for watching, and we'll see you in the next video. Bye-bye.